voltage drop testing. So I sent you guys out some sheets that we're going to do in class today on voltage drop testing. So what voltage drop testing is using the principle of Ohm's law and the fact that we know that current times resistance has to equal voltage. So voltage drop only happens in a complete circuit as current flows through resistance and work is done. In other words, the voltage is converted to work, heat, light, motion, force, etc. Voltage cannot drop in an open circuit, although an open circuit tests to have their place. So in an open circuit, I'm still going to do a voltage drop test, but what I'm measuring is voltage potential, not actual voltage. I can do work, but it will find where the open in the circuit is. So voltage drop can only be measured in a complete circuit. If the circuit is complete, then you're measuring voltage potential, not drop. Although a lot of times we don't necessarily distinguish between the two, is in the exercises we're not going to. So here I'm measuring voltage drop. I'm measuring the difference in voltage between two places. In this case, battery ground and the power side of the light bulb. And it says my difference between those 2 points is 12 volts. Remember, our meter always measures the difference. If I go to here, now I'm on the ground side of the light bulb, but my switch is open. So I still see a difference of 12 volts. Now, if I close the switch, I should see 0 volts on the meter, because then they would be electrically the same, so there'd be no difference.
Can I verify something so I'm understanding? If you close the switch, it becomes a conductor.
Right. Well, if I close the switch, it becomes a complete circuit, right?
Right. So you wouldn't really be testing it at that point, only to see if there's any voltage drop with it closed, right? And then you'd start deciding, is it the switch or back?
Exactly. So here I know I should have 12 volts with the switch open. If I close the switch and I still have 12 volts, either I have a bad switch contact or maybe the ground's not connected. Right? So
yes.
Right. So that comes back to our switch power and our switch ground. This is a switch ground circuit, and that the switch is on the ground. So the part between the load and where I'm touching right now is going to change its condition between having battery voltage present and having ground present based on the condition of the switch. And so that's how we verify whether a switch is working. So I could use an ohm meter, in theory, to see if a switch works, right? Is it open or is it connected? But an ohm meter flows such a small amount of current through it that an ohm meter might say, hey, the switch is connected, but when I try to use it and I try to flow enough current to make the light bulb light up, the light bulb's not going to light up, and the switch will actually test open, or test is not, connecting to ground. And that's why we use voltage drop to find these problems and not an ohm meter.
In this situation, when you have the switch closed, the voltage would be 0 because the current has gone through?
Yep, it should be 0 because the ground here on this side of the load should be electrically the same as the ground at the battery.
Question, Mr. Jackson. Mr. Brian. It's 12 volts passing the bulb, then goes to the switch. Switch is closed. There's no ground. What happened?
Right now, there's no ground, so I can only drop voltage through resistance if I have current flow. In an open circuit, there's no current flow. So I'm going to see this voltage potential on the negative side of the bulb all the way to the open, because I can't use any of that voltage in the bulb because there's no current flow. In order to use the voltage in the bulb, I have to have a complete circuit where current is flowing.
So when the switch is closed and the current goes to the bulb and goes to the ground, you mean to say the voltage passing the switch, which is closed, is 0. That you mean?
Well, if I close this, then the bulb is going to use all my voltage. So it's going to use all the 12 volts. So I would have 0 volts left after the bulb once I close.
That's what I want to know, Mr.
Yep.
Brian, because
Exactly.
also maybe we confuse the bulb maybe only consume 6 volt.
Right.
You know, so there's another 6 volt coming out.
Right. So the bulb has to use all 12 volts. If it doesn't, that means something else in the circuit, a switch or a connection or something is using some of that voltage through resistance. So another way of looking at this is that if I have a water system and I have a valve that leaks, so I put a cap on it. Over time, even with a real slow valve leak, that restriction, the pressure is going to be the same on both sides of the valve because there's a cap here. The cap is now providing the stop, right? So even though the valve might be closed or it might be open, it doesn't matter. I'm going to have the same pressure either side of the valve. As soon as I take the cap off, now if that valve is only open a little bit, I'm going to get an initial bunch of water, and then I'm going to get what? The little bit of dribble from the valve not being open. But if I put the cap back on and wait, what happens? The pressure will be the same both sides of the valve again. Same thing's true with electricity. So when I first connect to this, I'm actually going to get a surge. We call it a voltage surge or voltage spike. And then it'll settle down to the amount of flow that's controlled by the resistor, in this case, the light bulb in the circuit. So some specifications. And so like resistance test, the decision as to what is good or bad changes based on context, basic voltage drop specifications. And this is for the real world, not for our exercises. Again, I like easy math, so we're not going to use them in the exercises. But a switch is allowed 300 millivolts. So relay contacts are considered switches, so are solenoids. So if I'm dropping more than 300 millivolts of a switch, I need to be concerned about that. Is that the problem with the car I'm trying to fix? Maybe, maybe not. But if I have a starter that doesn't work, and I'm dropping 350 millivolts through the ignition switch instead of 300, that's not why my starter's not working. Okay. So it has to fit what the symptoms are and what I'm trying to do. So you kind of got to keep things in perspective. So like when we look at wire, it's a 200 millivolt maximum. The exception to that is our battery cables. They're allowed to have a higher amount.
Excuse me, Mr. Brian, maybe this is a stupid question. I encountered a question in the quiz. I think I answered 400 MV. Why is it that the M is capital over there and V capital over here? M is not capital.
Capital M, doesn't it stand for mega?
If it's a capital M, it's mega. A small m is milli.
Oh, okay.
So that's why my little m isn't capital.
That's good. We know.
Yeah, that had a big difference. So wire is allowed at 300 millivolts is the same as 0.3 volts. So 200 millivolts is the same as 0.2 volts, or 100 millivolts is 0.1 volt. So when we look at wire, we're allowed 200 millivolt max. Again, the exception, battery cables are allowed a little bit more. Normally we figure about 100. Connections are allowed about 100 millivolts. Module connection, 10 millivolts. So we're very sensitive to voltage at the module. But you can see it's not uncommon that, by the time I go through some connectors, go to my ignition switch and go down to my starter, I might lose 0.7 of a volt. Because, right, it's cumulative. I got wires, I got connectors, I got all these things. So even if I have an ignition switch that might be a little over, maybe my wires and connectors are under. So the total voltage that's getting there is what I would expect to get there. Therefore, it can't be my problem. So, if I have an ignition switch dropping 700 millivolts, that's definitely a problem because that shows me the switch is worn. And even if it's not the problem today, it's going to be a problem in the near future. So I'd want to let my customer know about that. But this is just kind of some good numbers. And these are all for circuits that flow 1 amp of current or more. which I have on this slide. What is the maximum amount of voltage drop that is allowed to be present across switch contacts?
300.
300 millivolts or 0.3 volts.
I get that.
How do I get that?
It was on the previous slide.
It was 2 slides ago. I can back up. Right here, switch. Switch or switch contacts. The switch contacts are the part of the switch that actually makes the electrical connection. So it's the same thing. Yeah, I usually don't put questions in here that I don't have on the PowerPoint. That'd be just unfair and sneaky. So here I'm doing a voltage drop test back to ground, and I can see I have 12 volts to the switch, but only 11.8 volts to the light bulb. That means that we had to have used 200 millivolts between the 2 test points. Everyone following me? So now my light bulb's only getting 11.8 volts because something used that voltage. We started with 12. I'd like it to get 12, but it's only getting 11.8. So when I use the meter here, I can see I got 12 volts all the way to here, but I only have 11.8 volts here. That means somewhere between here and here, we're using 200 millivolts. Now that's across the switch contacts, and that's what within specification, we're allowed to do that. But here I'm testing the ground. Another way of testing is between 2 points. So here I'm between, which is what we're going to do today. So here I'm between the battery and the switch, and then I'm between the switch and the light bulb. So between the battery and switch, I got all my 12 volts. Between the switch and the light bulb, I'd like to see 0, but I have 200 millivolts. That means we use 200 millivolts between here and here, or the difference in voltage between these 2 test points is 200 millivolts. Remember, our meter only measures the difference. So even though this is all on the positive side of the light bulb, and even though we've already proved we have 11.8 volts on this wire right here, and we have 12 volts over here, the difference between that 12 volts and that 11.8 is 200 millivolts. So that's what the meter is going to read. So this is why we would put a meter where the positive and negative leads are both on the same wire, because we want to measure the resistance of the wire. And the nice thing about this, unlike using an ohm meter where I would need to disconnect the wire to measure the resistance, here I don't have to disconnect anything. I need a complete circuit. So I'm doing what's called back probing, where I'm actually going to go into the back of the electrical connector with a fine pin and connect the meter that way to see how much voltage is being used. And this has the advantage of not disturbing pins and connectors and things like that, as well as it's very, very accurate to how any problem is going to affect the circuit we're diagnosing. So the key thing about a meter to remember is it measures the difference, not the absolute. The other neat thing about this test is that if I have a load, in this case, my light bulb, and I just go to the light bulb with it plugged in and I double check, I back probe the negative and back probe the positive, I should see all my applied voltage. I should see 12 volts. The mistake a lot of people make is they unplug the light bulb and then check for 12 volts. Well, if you do that, we're checking for voltage potential, not actual voltage. So therefore, I might put a light bulb in and it still doesn't work. And you unplug it, you check, and you got 12 volts, but the light bulb doesn't work and you're really confused. That's why we always back probe things, because I have a complete circuit. Ohm's law says that if I have one load in the circuit, it should use all, excuse me, of the available voltage. And this proves that it does. The other neat thing about doing this test is I'm going to get the same 12 volts whether my load is good or not. So if my light bulb works, I'm going to see 12 volts. If my light bulb's burned out, I'm going to see 12 volts. So I can convert this over to what? A motor, right? If my motor's working, I'll see 12 volts, but if my motor's not working, I'd also see 12 volts, or a solenoid or a relay or anything else we use on the car. So this is really great because by back probing it with everything connected, and if I have all my voltage, in this case 12 volts, and my light bulb, motor, solenoid, whatever it is, doesn't work, it's bad. Or the connection where it plugs in that I'm back probing at is not connected. That's it. There is no more diagnosis on the system. I've just proved that it has to be that part. So it doesn't matter if it's a solenoid in something like a transmission or whether it's your windshield wiper motor. If it has all the voltage to it and it's not working, it has to be bad. And the only way to check that is by back probing it, not by unplugging it. Yeah, go ahead.
I have a question, Mr. Perrin. Okay,
Sure.
we're talking about back probing. Is that why you got the wires crisscrossed?
They're crisscrossed so that the black is at the ground side of the circuit and the
Okay.
red is at the positive side of the circuit. One of the things the book talked about is the plus, and most meters don't give you a plus, but they will give you a minus. So if I put the leads backwards, I would see minus 12 volts. It would still be a 12 volt difference, but the meter would be telling me negative because I put the black lead on the positive side of the circuit and the red lead on the negative side of the circuit. I do have a
Okay.
nice video when we get into sensors. I think it's in module 5 where I really demonstrate back probing it and actually doing it. So this is kind of, why would I worry about looking up a specification and using an ohm meter to measure a solenoid or a relay when I can just check to see if it gets all 12 volts to it? And if it gets 12 volts to it, it doesn't work, it has to be bad. Why would I do a resistance test on it? A, it's a waste of time, and B, it's not going to really tell me anything. This tells me all I need to know. It's got power and it doesn't work. And you think about it, don't we do that at home all the time? If I plug the microwave in and the microwave doesn't work, and then I unplug the microwave, but I plug the toaster into the same outlet and the toaster works fine, do I figure out the microwave's broken?
Yes.
But I don't know how the microwave works inside, but yet I was magically able to figure out it's broken, right? Yeah. And I did that by what? Proving that it has power by using a different load. So I don't need to know how the microwave works to know it's bad, right? Because I plugged it in, it doesn't work, and I plugged the toaster into the same outlet, and the toaster made me breakfast this morning. So my microwave's junk and my toaster works great. And I don't know how either of them work inside. I don't need to. So that's what this test allows me to do, is it allows me to test a load by verifying it has power to it. And I can only do that with the load plugged in. Once I know it has power to it, and if it doesn't work, guess what? It's bad. I don't care what it is or what you call it. Isn't that a lot easier than taking things apart and testing parts and going, well, this part's in specification or it's out of specification, or worse yet, I'm allowed 8,000 ohms and it's at 8,050 ohms. Does that mean I replace it? Right? I mean, you're just being invited to make really bad decisions. So that's really the power of this, but the trick is to have everything plugged in. So in a series circuit with a single load, the voltage drop will be the same across the load, whether it's working or open. Is that true?
True.
True, and I just showed that. And that is one of my secret weapons of fixing cars right there. That little trick has fixed more cars for me. And I wasn't taught that in school. I had to figure that out. In school, they taught us to take everything apart and put an ohm meter on it. And I really struggled fixing cars. Once I figured this out, it got a whole lot easier. So here's our exercises. So what we're going to do is we're going to, and I sent everyone copies of this. If you don't, excuse me, if you don't have it, that's okay. You're not sending it back in, but I wanted you to have something in writing that you could either use online or use on paper as we go through this. So remember, my voltmeter reads the difference. So if I look at number 1, what should my voltmeter read?
Should be the 12 volts, right? Like you said, it's the
Correct.
voltage potential.
Voltage potential, because I'm on either side of my circuit. So the first thing I need to do is figure out where my circuit divides. In this case, it divides at the open switch. If the switch was closed, then it would divide at the load, right? So if I have if my meter is on both sides of the divide, or both leads are on the same side of the divide, they should be electrically the same. It would read 0. If they're on different sides of the divide, that means they're electrically different. So they have to read what that difference is. Another way of thinking about it is if I take the red lead, what it reads is 0 volts, and the black lead, which reads 0 volts, and take red, subtract black, and here's the difference. So I've tried several different ways of explaining this. But number 2, what's number 2 going to read?
12.
0.
Okay, I'm getting both answers here. So let's think about it. We know we have 12 volts from here all the way to the edge of the switch. So if my red lead measures 12 volts and my black lead measures 12 volts, what's the difference between those two?
0.
0. Remember, my meter reads the difference. So what's number 3 going to read?
12.
I'm sorry, what?
12.
Well, let's use our system.
12.
This is all 12 volts, right? If my red lead sees 12 volts and my black lead sees 12 volts, what's the meter going to read?
0.
0. How about number 4?
0 volts.
0.
0.
Well, think about it. My red lead is what? On 12 volts. What's my black lead on?
At 12 volt.
Black's on 0, isn't it? Because I have ground here, comes through the light bulb all the way to here. We're separating at the switch.
So it is 12 volt.
So it's
It should
12.
be 12, right? Because it's 12 volts here minus what the black lead says, which is 0. So 12 minus 0 is 12. So what's number 5?
12.
12.
Yeah, it has to be 0, doesn't it? Because I only have 12 volts up to the end of the switch. I'm on ground here. I'm on ground here. So 0 minus 0 would be, how
0.
about number 6?
0.
0.
0, right? Because it's
Zero.
electrically the same. How about 7?
0.
0. Okay, now that you got this down, let's close the switch.
So Ryan,
Brian, I got a question.
Yes.
I didn't get why number 2 and 3 got 0.
Okay. So what is my red lead reading right here on number 2?
It's supposed to be 12, no?
Right? And what's my black lead read?
It's supposed to be 12, no?
Yep. So if we take 12 minus 12, what's that equal?
0.
Okay.
0. Right? Hold on a sec.
Yes, maliit ito eh.
You unmute. Mute.
Okay.
so Ryan,
Yes.
in what page number are you right now?
What number am I?
Yeah, for the PowerPoint.
Oh, which slide number?
Yeah, yes, please.
Oh, good question. I need to back out to see that.
It's
I'm
just that
probably up around 36, I think.
oh, okay, yeah, because I'm on 38, and yeah, the everything is like the same. The multimeter is actually in the same place, but I see that the switches on some are closed.
Oh, so you're
That's why I
one
got a
slide
wrong
ahead of
answer.
me. If you back up a slide, So I'm on the first slide of these. There's 5 slides. So the first
Okay.
slide has the switch open.
37. Okay. Okay. All right. Thank you. I was wondering why did I got the answers wrong, but okay, I see why. Thank you.
Yeah, there's 5 slides, and so that's really okay. So number 2, so number 3 is the same thing. I have 12 volts here, and I have 12 volts here because my switch divides the circuit. The switch is open. So everything from here to here has 12 volts. My meter reads the difference between the 2 spots I'm measuring. So what's the difference between 12 volts and 12 volts?
0.
0. So, for example, you can see where this is, again, this is why we call it voltage drop. And this is a little, excuse me, people struggle with this concept because we think of the meter reading an absolute. It tells me there's 12 volts there. No, what the meter does is it measures the difference. It measures a difference between the 2 points of measurement. So, if
You
we-
know, the exercise sheet you sent, there, it's not colored. So, I mean, they're
Okay.
all, that's why I was.
They're
getting
not.
con-
I will have to recheck that. I could have sworn I sent colored sheets. So thank you for letting me know that.
Mine is black, all black.
Yeah.
Yeah, because I started with the colored sheet. So maybe when I saved it into PDF, I might have had it flipped over to black and white. So I apologize. I did not know that.
No.
I will have to fix that. What I've had students do in the classroom, and I tried doing it on the PowerPoint, and it just looked horrible, is they actually took 2 highlighters, and they took a red highlighter and like a black highlighter or a green highlighter, something different. And that way, and they use that to divide the circuit. And then based on where the meter was, and unless the meter was on both the red and the black, it couldn't read 12 volts. If it was on both red or both black, it has to be 0 volts. So that was something people did in class using the highlighter that worked pretty good. But I tried doing it on the PowerPoint, and it really totally confused and messed things up. So here I've closed the switch. So now what divides the circuit? Where's all the voltage going in the circuit now?
The load?
The load, right. So my load divides the circuit. We only have one load. So we know that on one side of the load is positive, the other side of the load is negative. So here I have a voltmeter on both sides of the load. So what should it read?
0.
12 volts.
12 volts, right? Because I'm coming from battery positive to ground. The difference between ground and battery positive is 12 volts. What should number 2 read?
0.
0, because right, this is all positive voltage all the way over to here. So 12 volts minus 12 volts is 0 volts. How about number 3?
0.
0. How about number 4?
0.
0.
0, right? Because I'm still have 12 volts because we're dividing at the bulb. How about number 5?
0.
How about number 6?
0.
12.
12, because my bulb is using all the load. And how about number 7?
0.
0.
Okay, so we know from our rules that my load should use all 12 volts. So if I went to the bulb and it only had 10 volts, then I would use voltage drop to go between power and battery or between ground and ground like this last test to see where the voltage is. So for example, if I only had 10 volts here and I do these other tests and I found that, whoa, I got 2 volts when I go across my fuse. Well, I know it should be 0, right? So if I have 2 volts here, what else is here? Resistance, excessive resistance. That's where the voltage went. So I could have excessive resistance here on the power side, or I could have excessive resistance on the ground side. But when I add all these up from number 2 through 7, when I add them up, they have to equal 12 volts. We know it should all go through number 6. But if number 6 doesn't have my 12 volts, that means somewhere else here stole my voltage.
Sir
And
Brian, number
what's
6,
that?
your question.
Yes.
12 volts is the source, then goes to the fuse, then goes to the switch, then
Right.
goes to the bulb. So 12 volts consumed by the bulb. Why is it the outside, the coming to the ground is 12 also? It's supposed to be less than 12 because it uses the bulb.
Right. Right now it's working correctly. But if my bulb only had 10, maybe I'm using 2 volts on the ground because I have a bad ground connection or a bad connection in a wire or a worn wire. Remember, I have to use all my 12 volts in my series circuit. If I have more than one load, don't I have to divide the voltage? So even though he's supposed to get all 12 volts, if someone else has resistance, they're going to steal some of his voltage. Are you following me? So when I add up steps 2 through 7, they have to equal 12. If the system's working right, number 6 is the only one that'll use voltage. But if number 6 doesn't have all the voltage, that means someone else had to have stolen it. Oops.
So number 6 is number 1, like the same.
Right, because both of them are on what? Either side of the load. They both show me that this shows me the circuit is using all the voltage. This proves that it's the load using all the voltage.
Thank you, Mr. Brian.
Yeah, you bet. You know, this is kind of hard to get our head around a little bit, but this is how we actually fix cars. This is actually how we find problems, is by voltage drop testing, because we're looking for where the voltage is. So now I'm going to make it hard. I'm going to put in 2 loads. So the first question I have is the switch open or closed?
Open.
Open. If it's open, is there any current flow?
No.
No. So that makes this a pretty easy sheet if we follow the rules we've already learned. So what is voltmeter 1 going to read?
0.
Oh, right.
Oh.
Because they're electrically the same. There's no current flow. The switch is open. The switch is dividing the circuit. Unless I'm on either side of the switch, it has to be 0. So what's number 2?
0.
How about number 3?
0.
How about number 4?
0.
Number 5?
12.
0.
Well, right, because we're on either side of the switch. The switch divides the circuit. How about number 6?
0.
0.
How about number 7?
0.
0.
So it doesn't matter how big my resistors are or how many of them they are. If it's an open circuit, they can't drop voltage. They have to be electrically the same. Now let's close the switch and do some math. So in order to find out what the answer is for number 1, what do I got to do? I have to figure out the total resistance of the circuit and take my voltage divided by resistance to come up with current flow, my amps, and then take my amps times my resistance to get my volts.
This one is gonna be 6, no?
Yep, gonna
Yes.
be 6. I will give you a clue. This entire page all adds up to 12 on the resistor, so your current flow is the same everywhere. Remember, it's about ideas, not math. So what's number 2 then?
4.
6.
4, right? Because I have a total of 12 ohms of resistance. 12 divided by 12 is 1 amp. 1 times 4 is 4. What's number 3?
10.
10.
I think I need glasses. I didn't see the
Oh,
numbers.
sounds like a lot of people need glasses all of a sudden in this class.
Yeah.
What's number 4?
6.
6.
6. And what's number 5?
0.
0.
0, because that should be electrically the same. How about number 6?
12.
12.
12, right? Because I'm going across 12 ohms of load. How about number 7?
12.
12. There we go.
12. 12.
Now we're going to have a little fun. What I've done here is I've added extra resistance. I got 4 ohms resistance at the ground. I have 4 ohms resistance in the switch, 4 ohms resistance in the ground, and 4 ohms resistance in the wire. So let's figure out, let's take a couple minutes and figure out. So when you do to figure your current flow, make sure you add our extra resistance into your total resistance of the circuit to figure current flow.
First
Well,
one is
guys-
3, huh?
Give you guys a minute or two to figure out 1 through 4 here, and then we'll go over them.
First one is gonna be 8.
Yes. First one is 8. I'm going to hold off on giving you the rest of them till more people get a chance to get it, but that way you know the thought process is correct.
You get it 8, Mr. Bryan.
You explain how he got.
Okay, so what he did is he took the total resistance, which is 12 ohms, divided by 12 volts, which gives you 1 amp. The voltmeter is going across 8 ohms. So 8 ohms times 1 amp has to be 8 volts.
Read it again, sir.
So that's how we got number 1.
Did you say it again, Mr. Bryan? Some people cannot hear.
Oh, some people can't hear?
7 amp,
Yes,
let's say.
please.
For number 2,
Okay, number 2, what'd you guys come up with?
7.
Not 7.
4.
3.
I did hear a right answer in there somewhere, so let me walk through it. What's my total resistance?
8.
8.
8? Isn't 4 plus 8, 16?
16.
16.
12 divided by 16 is what? 3/4 or 0.75? So what's 3/4 of 4 or 0.75 times 4? 3. What did we come up with for number 3?
4.
4. Oops. How about number 4?
And
4.5.
4.5, because we have 16 ohms of resistance. 12 divided by 16 is 0.75 or 3/4. And if I take 0.75 times 6 or 3/4 of 6 is 4.5. So what we did here, we know from the previous slide that if I had 2 loads in series, that they should be using all the 12 volts. Well, here, because I have 4 ohms of resistance on the ground, they're only getting 8 volts. Well, if these were fans to keep my engine cool, would that mean they might be turning slower? If they're light bulbs, would it make them dimmer?
Yes, I think so.
Yeah, so you can see where I might have a car that's overheating, even though someone's put a lot of parts into it because they're guessing. And the root cause is actually a bad connection to the ground or a bad connection in a wire or at a switch, causing the voltage to be lower. If the voltage is lower, the fan's going to spin slower and the car might overheat. So you see why it's not as simple as just putting parts on the car. It's about the electrical testing. That's why it's so important to verify that the correct voltage is available to the load. Now, I also like this exercise because we're only using a 4 ohm resistor. And GM says that as long as it's 5 ohms or less, it's not a problem. And this exercise really proves that GM's wrong, and GM's a big company. But if I have 5 ohms of resistance, it's definitely going to affect how the circuit works. And we really see that here just by doing the math. So resistance testing, an ohm meter or the ohm meter function. Actually, let me back up a second. So was it helpful going through these voltage drop exercises with you guys?
Yes.
Okay, because this is really all about figuring out test point voltages. What should the voltage be? And I know we talked about that at the beginning with our fan that was going around, but we're going to see this concept and how resistance affects it throughout the class as we look at more and more circuits. And especially when we look at circuits with problems and how we can see this where we might have a problem. What I'll tell you is most of the electrical problems on the vehicle are either caused by a failed component or excessive electrical resistance in the circuit. So we rarely have a short. We don't have that many opens. We have a lot of excessive resistance, a lot of bad connections. So
Brian?
on the car, this is the most common thing that we're actually diagnosing in the electrical. Yeah.
Can you please go just one more time on number 4?
Number 4, sure.
Yes, please.
So I have a total of 16 ohms of resistance, right? The 4 plus the 6 plus the 6.
Yes.
So I take 12 divided by 16.
3/4.
And that's 3/4 if I reduce it. And if I want to make it a decimal, it's 0.75. So then I have to just take which is my current flow. So now I'm going to take that 3/4 or that 0.75 and multiply it times the 6 ohms that my meter's reading across. So 0.75 times 6 is 4.5. Or if I want to divide 6 into 4 parts, each part would be 1.5. Right? So I got 3 1.5s, which is 4.5. A couple of different ways you can get there.
Okay.
Mr. Brian, well, we're talking about measuring voltage, but most of the repair people that I've seen are not using DOMs. They're using test lights, which you can't measure voltage on. So are they just doing it wrong for my whole life?
Yeah, if they're still using a test light, they're definitely doing it wrong. We normally use power probes now. And the newer power probes will actually give you a voltage reading on the display. So what they used to do in the old days is they'd use a test light because it
Now you call me old.
parallel circuit. And the test light puts a load on it. So if the test light didn't light up, that meant I didn't have good potential there. And so I used a test light for probably the first 20 years or so in the industry. Was my go-to diagnostic tool. 2 issues with the test light, traditional test light. One was since they created a parallel circuit, they could actually change how the circuit works while you test it. And if you used them on the wrong computer circuit, you could actually damage a computer to the point where it didn't work. So that's why test lights really fell out of favor, as well as you were really relying on how good a ground connection you were able to make. But no, I still own several test lights, and they were my go-to tool for probably the first 20 years in the industry. I fixed a lot of cars with them. But what we found is that I can have something light up with a test light and still not necessarily operate a load, or especially with computers, I'm losing enough voltage where the reading the computer's getting is not accurate. And that's why we don't use test lights on those circuits.
Thank you.
Can I ask one question?
Only one, Warren. That's it. Then you're done for the day.
Then I'm done. If I was testing, now this kind of confuses me. I might have the numbers wrong. If I was testing a negative cable from the battery post to the ground that it's connected to, I should, with a multimeter, I should have 0, right?
While the engine's cranking, ideally you would have 0. You're allowed 0.2 volts or 200 millivolts. And you have to do that while the engine's cranking, because that's the only way you put enough of a load on a battery cable to actually voltage drop test it. It's like having a freeway. I can't tell how good the freeway is by having one car go down at midnight, right? Let's see how it handles rush hour traffic. Then we know if the freeway can flow enough current. Did I answer the question okay, Warren?
That should be 12 volts with the, after, if it's just sitting key on, engine off.
Key on, engine off. Doing a voltage drop test, you still see 0 volts on the battery cable.
Okay.
Right. Now, if I'm talking the cable that attaches to the starter on the starter side of the solenoid, then yes, I'd see 12 volts key on, engine off, and then I should drop to 200 to 500 millivolts cranking. But that's on this. That's because you're after a switch, and we'll get to that in the next when we get into starters here in the next module.
Okay, thank you.
So Brian,
Yes.
question.
Yes.
Can you explain me a little bit the number 4 again? I don't get where you come out with the 4.5.
Okay. So I have 12 volts. And what's my total resistance in the circuit?
16.
16. So 12 divided by 16. So voltage divided by resistance will give me current flow. So 12 divided by 16, if I reduce that down, I can make that 3/4, right?
Yeah.
Or I can just do the math with a calculator and come out with 0.75, either way. So if I take 0.75 times 6, which is the only resistor I'm testing, I'm going to come up with 4.5.
All right. Got it. Thank you.
You bet.
So the rule is divide voltage first by ohms, right? Because I did it the opposite, and that's why I got the answer wrong. I'm like, okay.
Yeah. If I want to figure out the voltage drop across multiple resistors in a series circuit, I have to first figure out the current flow of the circuit. So you figure current first, then I use that current to go back with each resistor to figure out the amount of voltage each resistor uses.
Thank you, Mr. Ryan.
You bet.
Mr. Brian,
Yes.
this is Del. How come I understand this last slide better than the first however many we had, first 3 or 4?
Maybe because you learned something on the first 3 and 4, so now the last one's easy?
Oh, I don't know. I still am going back there and I'm like,
Well,
I
let's go
don't
back
get
a
some
little
of
bit
them.
then. Oops. Let's see, do I have slice order here? So I'll go over this again. So here's our first one, right? Our switch is open. So our circuit divides at the switch. So in order to read 12 volts, my leads have to be on either side of the switch. That's why all the rest of these read 0. Are you following that, Del?
Say that again, please.
I'll try. I said my switch divides the circuit. So if I go up and down, the switch is the difference between positive and negative energy. So in order for my voltmeter to read 12 volts, it has to be on both the positive and the negative side of the switch. That's why I only have 12 volts at number 1 and 4. Everyone else is on the same side of the switch. So when my meter checks, there's no electrical difference between the 2 points that are being measured. And that's why that's 0.
Oh, so that's a trick.
Yeah.
Oh, I didn't get that in the beginning. All right.
Okay, right. So now when we close the switch, the load divides the circuit. So now unless I'm on either side of the load, I have one on the positive side and the negative side of the load, I can't read 12 volts. That's why I have 0 volts here, 0 volts here, 0 volts here, 0 volts here, but 12 volts here because I'm on either side of the load, and then back to 0 volts. So since the load divides the circuit, I need to be on both the positive and negative side of the load in order to read 12 volts. If I'm reading on the same side of the load, I should see 0 volts because there should be no electrical difference between these 2 points.
Yay, okay, I got that too.
Okay, good. And then when we did this next one, the switch is open. So again, my switch divides the circuit. So the only place I can read voltage is where my meter is on both sides of the switch, right? So these other ones have to be 0. I don't even need to look at any math. This goes across the divide in my circuit, the switch, it has to read 12 volts. And these next two have to be 0 because what? This is all on the ground side. There's no electrical difference between here and here. So it doesn't matter where I measure, it has to be 0. Here I have an electrical difference because I'm on the positive side and the negative side of the switch. Once we close the switch, now I have current flow. So I have to do what we did on the last slide. I need to figure out my total current flow, which in this case, I have 6 ohms plus 6 ohms is 12 ohms. 12 divided by 12 is 1 amp. Then I take my amperage times my resistor, gives me my voltage. Because all my voltage is used by my loads, in this case, my 2 loads. So here, these all have 1 amp, so I would take 1 times 4 ohms for 4 volts, 1 times 10 ohm for 10 volts. So you can see where, based on the size of the resistor, changes the amount of voltage that load's going to use. And so those slides I showed last week on the light bulb with the marker light and the tail light, and they kind of do some magic there. That's because of the different size of resistance. They can control who's going to get 10 volts and who's going to get 2 volts. So which light bulb is going to heat up and which one's not going to heat up and those kinds of things, because they're splitting the voltage. So this is how we split the voltage in a 12 volt circuit, is by using different size resistors. So number 4 is going to be 6. 5 has to be 0 because there's no electrical difference. This is all on the power side. And then here we're going across all of my 12 ohms, so it has to be 12 for both of those. And that brought us to our last slide that we just did.
Thank you very much.
You bet. Yeah, this is a tough concept. People really struggle with this, and I'm not talking about just, students at the entry level, but also even advanced level. I have students really struggle with this. But what I can tell you is the students that really struggle with this, that are in the field, that are working as technicians, are the same ones that really struggle with fixing electrical problems. So this is a real key thing for helping understand how to effectively use the meter to trace electrical problems and figure out electrical problems. Especially, like I said, the most common problem that I diagnose is high resistance. Someone brought up a test light. A test light works great if I have an open circuit, and it works okay if I just have a bad load. But if I have high resistance, the test light doesn't do that well. So the ohm meter function in a DVOM only works on isolated wires and or components. Components must be tested, disconnected, and wires must be isolated at both ends. So in this example, we're testing a wire. So we had to disconnect our injector and disconnect our wire and harness from wherever it connects. And then I could use the ohm meter to test the wire. Now, keep in mind, my ohm meter doesn't flow enough current to accurately test the wire. So I could have just that one strand that I showed you that the ohm meter is going to say is great. But when I plug it back in this case, my fuel injector still wouldn't work. So that's why a couple reasons why we don't do this is, one is it's not accurate. The other is it's time consuming. I got to unplug everything and test things one at a time. Why would I want to take a whole car apart just to test things?
Ryan?
Yeah.
And is it the same result if we use an amp clamp?
An amp clamp is going to give me current flow, and then from there I can infer resistance. So absolutely. A lot of times what we do is we use an amp clamp as a high level tool. So an amp clamp is going to tell me if I have a potential problem. Once I suspect I have a potential problem, then I would use voltage drop testing to isolate the problem, right? Because the amp clamp is quicker than the voltage drop test, but it's not going to tell me specifically what's wrong. It's just going to tell me something's wrong. So for example, if I use an amp clamp and I have low current flow, that means I have to have high resistance. Well, is that high resistance in the injector? Is it in the wiring? Is it in a connector? I don't know. Remember, our current flow is the same throughout the circuit. So the amp clamp kind of sets the alarm. Hey, this is too low. We have high resistance here. Now I need to go in and do voltage drop testing to find out, hey, is the fuel injector bad or do I have another problem in the circuit? So we use them in conjunction. Great question.
No, it's good. I was, it was just like, I was working it on my mind, how, that
Yeah.
could, work. Yeah, okay. That makes sense. Thank you.
Right, and you hear me talk about high-level tests in this class. Using an amp clamp can be a high-level test. And one reason why we call it a high-level test is because it's quick to perform, and it quickly tells you, is there a problem here or not a problem here? But it doesn't tell you specifically what the problem is without more testing. But high-level tests have their place because they allow me to prove something's not the problem very quickly, as opposed to going in and doing all these other tests.
That question illustrates what you're saying very clearly. Thank you.
You bet. So here is an injector resistance example. Here we're measuring out the resistance on an injector. So, say I used an amp clamp and saw that I didn't have enough current flow. I could disconnect the injector and measure the resistance, but keep in mind the resistance is going to change between testing it here and when it's working. That's why we would use voltage drop, because then I could back probe it and go, wait a minute, if I have all my 12 volts going to the injector, but I'm not flowing enough current flow, the injector has to have too high a resistance. You see how I can figure that out using volts and current without actually measuring resistance. And that's what I mean by we really don't measure resistance that much anymore because things change. Resistance changes as things get hot. My fuel injector may have a resistance problem when my car is running at 200 degrees, but it may test fine at 68 degrees when it's cold enough to take it apart and get my hands in there to test it. Right? Because, we know resistance change with temperature. So that's another advantage of why we always want to test things when they're complete. I put these in here to show what I mean by isolating something completely to test it with an ohm meter. So in order to use an ohm meter, the component being tested must be isolated from the circuit. Is that true or false?
False.
True.
True. Have to isolate it. So continuity testing, resistance and continuity testing should always be kept in perspective. An ohm meter will show you if a wire is bad open, but it can't distinguish degrees of good. So here I can see I have an OL for out of limit showing that this wire is open. But here on both these other tests, I show that I have continuity. So I could have a short to circuit or a short to ground, and it's just going to show me I'm connected. It doesn't tell me if I'm connected correctly. It doesn't tell me how well I'm connected. And so this is why we don't just use an ohm meter to find out if a wire is shorted to ground, because it's going to go back through all the different loads. And since the series are open, it's going to come out and say, hey, we're shorted, even though we're really not. And that's why we have to isolate and test one piece at a time with an ohm meter, which is why we just don't do it anymore. We use voltage drop testing for it, or we use current to see if we needed to use voltage drop testing. Like I said, occasionally you'll use an ohm meter for a component to test it or whatever on the bench. But if it's an actuator, why don't I just power it up and see if it works instead of measuring the resistance? Right? So why should I use resistance to infer that it should work when I can test it to see if it actually does work? One has guesswork. You're buying parts hoping for the best. The other one, So current testing, there are only two methods for measuring current: directly by placing an amp meter or the amp meter function on a DVOM inside the current path in series with the circuit, or indirectly by measuring the strength of the flux lines around the circuit with a shunt or inductive current probe. So most testing we do today, we use an inductive probe because it's less intrusive and it's quicker. And the flux lines are the electromagnetism that flows along the wire. And so if I'm going to use internal testing, Most meters have a 10 amp maximum. If I go over the 10 amp, I've just bought $30 worth of fuses. So that's the reason why we don't do this very often. If the current measured is expected to be over 10 amps or close to it, the internal meter should not be used or the fuse will be blown. And we have two settings here. I have a milliamp, an amp, and then I have a microamp, very, very small. And if you notice, these are both DC. That's why the lines are straight. If you look at voltage, I have a wavy line for AC and a straight line for DC. So here I have my milliamp microamp setting and my amp setting. So there's two different fuses in here. One's a 400 milliamp fuse. The other is a 10 amp fuse. So if I plug into here and I go over 400 milliamps, I just blew that fuse. If I go over 10 amps here, I blew this fuse. So we'd always want to start with the highest fuse. And then if I need to change scales or move down, then I would change fuses. But a lot of things I measure in milliamps, I'm actually reading about 600 to 800 milliamps. So I'd still want to use the amp setting. An inductive clamp, which I have here, is a little bit different. What it does is I'm able to clamp just around a wire. And then I have two scales on this one. I can say 1 millivolt equals 10 milliamps or 1 millivolt equals 100 milliamps. And what I do is I plug it into the voltmeter leads on my meter. So I'm going to plug it into my common and my voltmeter. I'm going to plug it into these two, not the amps. I'm going to turn my meter to DC volts. I'm going to read volts on my meter, but my volts are going to equal amps. So in other words, do I want 1 millivolt to equal 10 milliamps or 1 millivolt to equal 100 milliamps? So I can change the scale that I want to see the signal on. And then I basically have to what? Do the math. So this allows me to use this with any voltmeter or lab scope because I'm converting it to volts, which all the meters do. The other advantage of this is there's no fuse to blow. So you can see, even though these are around $100, how many times do you need to blow some fuses in your meter to pay for this? Right? So, you know, there's an advantage to that. Also, if you notice down here, says Cat 3, 300 millivolts plus or minus Cat 3. So this is acceptable for a lot of DC hybrid work going to the batteries. And let's see, DC, yep. What is the maximum amperage that can be tested through the meter before the fuse may blow?
Ten amps.
10 amps. And that is a need to know number. I'll tell you right now, there's not a lot of numbers that I really hold out that I expect you guys to know. This is one of them, simply because if we're in a lab and you do it wrong, it's a real expensive mistake. So here's a typical amp meter connection. So I've taken the fuse out. I've put the fuse into a fuse holder. So now I'm going through the fuse, through my meter, which has a fuse, through to the injector, through the PCM to ground. So you see, when we use the internal part of the meter, we actually are connected in series. It becomes part of the circuit. So everything we're trying to do goes right through the meter. It's connected in series. Unlike a voltmeter, we connect in parallel, right? We're connecting 2 points in the circuit, but there's no current flow going through the meter. So an amp meter must be connected to the circuit being tested in which of the following ways? Series, absolutely. Here, someone took the load out and put the amp meter in place of the load, and it made the amp meter very unhappy. Because what happens if I have a circuit, I try to build a circuit with no load? There's nothing to limit current flow. It's going to go until we melt something. In this case, we melted the little fuse inside the meter. We also can't connect it in parallel like we do a voltmeter, because what I've done is I've just created two paths of current flow, one through the fuse and one through the meter, so my reading will not be accurate. If I want to connect it with a disconnected load, then I would need to unplug the connector, in this case from the injector, because that's just what we're using. I would have to use a jumper wire on one side, my amp meter on the other. So I'm making two electrical connections in order to read how much current the amp meter is, the injector is using. So you see why going to the fuse or going some other place might be easier. Or easier yet, you'll see, is using a scope. When testing for larger amounts of current flow, what type of probe should be used? Inductive probe, number 2, absolutely. So now this is something else I sent out to you guys. This is a circuit tracing exercise. I got a couple different pages on it, and you can use a pen or a highlighter or whatever. I'm going to point out different parts of the circuit after we highlight it. But what we want to do is we want to come from battery power through position M1 in the switch. So pretend the switch rotated to M1 and get all the way over to turning my blower motor on and all the way to ground. So I'm going to give you guys a minute to go ahead and trace that out.
So Brian,
Yes.
when you said trace it, like do we have to do it on the computer, or should we supposed to print it out?
Well, if you could print it. If you're doing it on the computer, just kind of run your finger through and get a design. I'm gonna kick it up with colors and actually show you the circuit here in a second.
Okay, it's just that on the PowerPoint I didn't saw any option to print.
Oh no, I sent out the separate announcement last week with the PDF file with this.
Oh yeah, I saw that.
And I think it even got sent out again today on accident, but I'll go ahead and click this one so you can see what we're doing. So here we traced M1. So I've got power coming down to switched power in yellow through one resistor, through another resistor, through a third resistor, through the default position of the relay, to my blower motor, to ground. So where it's green is always going to have ground. Where it's red is always going to have power. The yellow is going to change its voltage based on the position of the switch. So if the switch is off, I would see ground potential all the way up to the switch. And with the switch on, as soon as I go to power, here I'm on M1, I'm coming down and I hit 0.8 ohms. Then I hit 0.3 ohms. Then I hit 0.1 ohm of resistance. Then I get to the motor. So each of these resistors has to what? Use some voltage. So this is why my blower motor goes slower. It's because we're using some of the voltage. That being said, if I traced from here and I went back this way, back through this 1.57 ohm, all the way to where it says low, I would still have all my 12 volts because I can't drop any voltage through this resistor in the M1 position because it's not a complete circuit. It's an open circuit. And this also really confuses people when they're testing. It's like I'm on M1, but I have battery voltage over here too. Why do I have battery voltage both places? I think that the resistor is shorted. No, this is open, so I can't drop any voltage through the resistor. So go ahead and trace. Let's move our switch to M2. And we can see here now on M2, I'm only going through this resistor and this resistor over to my motor, which means that now I would see, not only would I see all my 12 volts here, but I'd see it here and I'd see it here, because I can't drop any voltage through these resistors because they're not connected to anything.
Mr. Ryan,
Yes.
I'm sorry for keep asking. Do you mind if can we? Is there any way that we can see what will be the voltage reading on the M1 on on the blower motor?
Oh, on the blower motor itself,
Yes.
I could make something up. I don't know what the resistance of the blower motor is.
Based on the resistors that we have, like A, 3, and 1.
Right, but I don't know what the resistance of the blower motor is.
Oh, I see. Okay.
Right.
We need that information. Okay.
Exactly, because that's our main load in the circuit. I mean, I could make up some numbers, but they'd be completely made up. But yes, the voltage drops to the blower motor, so if I'm over at low, I'm dropping more voltage than if I'm on M1 or M2 or M3. And when I go to high, now I'm not even going through the resistor anymore. I'm going straight over here to turn this relay on. So the relay is now the load for that circuit. And then there's a separate power right here that comes on through the switched relay where it puts all 12 volts to the blower motor. And a lot of times what happens with blower motors is you'll lose the lowest speeds. So you'll lose like low and M1, but high works. That's normally caused by a bad blower motor resistor. Because you think about it, if the low stuff doesn't work, but the higher stuff does, that means it's electrically connected, right? So if M2, M3, and high all work, but low and M1 doesn't, that means odds are I have an open probably at this resistor inside the blower motor resistor assembly, because we know the motor's good. We know all this wiring's good. We know these two resistors are good. So if it works on 2 and 3 and high, but doesn't work on low and 1, odds are the blower motor resistor is bad. And that's a very, very common thing that happens.
A schematic would show the words low and high, or are these like the results of the probe?
No, your schematic, this is a schematic. This happens to be for GM. And you can see it says low, M1, M2, M3, and high. And I bet you your dial on the dash shows low, M1, M1, 1, 2, 3, and high. It probably doesn't have an M in front of it. It probably just has 1, 2, and 3.
Okay.
So this is going to mirror what you see on the dash of the car. And these are common. And again, this says HVAC for heating, ventilation, air conditioning control assembly. So this is a computer. So wait a minute, here's this complicated computer and it controls the blower motor. But when we get down to it, this is a pretty simple series circuits we're using, isn't it? Each of these is its own little series circuit. Nothing intimidating about that. And since I have several of them, I can compare them to each other and figure out what is working and what isn't working to figure out where the problem most likely is in the system. So there's a real world application of using what we've learned where we have multiple loads, or maybe only a single load in a 12 volt system. And depending on how many loads, we know the loads have to divide the voltage. That's what causes your blower motor to have a low speed, medium speed, and high speed in your car. So all this series circuit and all these resistors and all this other stuff that I've been driving you guys nuts with, you can see where we actually use it on a car. And like I said, very, very common system to have an issue. Here's a radiator fan circuit. This is a little more confusing because is this a series circuit or a parallel circuit? It depends. Because I have 3 relays, and I should highlight this out to show you, but I got ground here, which comes up and it's spliced for this motor. And then it comes to this relay. And then I have power here, and the power comes out to here, comes out over to here for the on off, and it comes into here for the on off. So if we turn this relay on, the left fan comes on and it has to get to ground. So if the relay is in this position, it's going to come over to here and it would have to what? Go through here to get to ground. Isn't that a long series circuit? So that means what? Each of these fans gets some of the voltage. So each fan would get half the voltage if they have the same resistance. But if I switch this relay, now I turn this on, and it comes over and it goes this way. Now it does what? Goes straight to ground. So this fan now gets 12 volts.
So Brian,
Yes.
I'm sorry for interrupting.
No
So
problem.
you mentioned that the ground for the first cooling fan, the ground goes through the motor.
Right.
So isn't it that the power has to go physically contact to contact because the motor is, the stator inside, it doesn't really close? You know what I mean?
Right. So you're going to have power. So if I was to do a voltage drop, so if it comes down through this motor to ground, there's two loads in a series circuit. So they have to divide the voltage. They're going to do it, proportionally based on resistance. Now I'm going to assume these are the exact same motor and they have the exact same resistance. So if I started with 12 volts, each of them would use 6 volts.
Okay.
And if they're only using 6 volts instead of 12, does that mean they're going to spin slower?
Yes, they should, no?
Yeah, right. So that's your low speed fan on your radiator. And then they switch it to two series circuits. Into parallel circuits into two separate circuits when they want high speed fan, and then they can control them individually.
I see. No, yeah, okay, yeah, it
Yeah.
makes sense now. I got lost there for a minute, but
No
now I know
problem.
what you're talking about.
And this is a little confusing, but I put it in here because this is GM, but so many manufacturers do this or do something very similar to this to get their low speed and high speed fans, where they're actually running them in series for low speed, and then they run them as parallel circuits for high speed. We see manufacturers do that with headlights. They're in series for the daytime running lights, but they're in parallel for the headlights, and it's the same bulb. So we do have these switch circuits that go between series and parallel, and we use relays normally to do that. So pretty cool.
Mr. Brian, for
Yeah.
a beginner, can you please explain what the relay is?
Yes, and I'm going to get a lot more into relays. So what a relay is, and I touched on this a little bit last week, it's a load for one circuit and a switch for another circuit. So what we do here is the low speed cooling fan relay control turns on, connects ground, and I have power. So I've ground here and power here. This is my load, and it's going to create electromagnetism. And we see these little dashes here letting you know that this electromagnetism is going to close this switch. So now I have power going through all the way to here. When we turn the relay on, the switch closes, and now power is able to come down to the cooling fan. So what we do with relays is we allow something like a module, in this case, a powertrain control module, to use a small amount of current to turn on something that uses a lot of current. And I'm going to actually get into relays. We're going to see what they look like inside and spend a little more time on the pins. But we control tons of things with the relays. Now, relays can be a 4-pin relay or a 5-pin relay. If it's a 5-pin relay like we have here, I have a leg here that's connected to the default position and a leg here that's connected when the relay is energized. So if I energize the relay, this is connected to K14. If I don't energize the relay, then it's connected to L12. And so this is my high-speed cooling fan. So the computer, again, is going to come up. And what it's doing here is actually turning this relay on and this
The
relay on
radiator fan.
both at the same time.
Sir, I
Yeah.
have a question. For the radiator fan circuit, can you enlarge the screen and use some red color cursor mouse so that I can see the changes or your cursor? I cannot see the cursor.
You should be able to. It's a regular cursor mouse on it. Do you have your screen minimized?
Very minimized. Can you please tell me how I can increase the size of this circuitry?
Well, you have little dots for your view, and you can change it from looking at me to looking at the PowerPoint that I'm sharing. Because I'm sharing this should take up almost your whole screen.
Correct.
So, Mr. Brian, is relay acting kind of like a switch?
Exactly. It is an electromechanical switch. So it's basically we use an electrical signal to turn a switch on. So we send the electrical signal to the relay, and then that switch turns on. So the relay is the switch.
In this schema, there are 3 different relays, right?
On this system, there's 3 different relays. So some systems use 4. I mean, there are different configurations, but we use relays throughout the vehicle. And the book talks about relays right now. I get into more on the PowerPoint coming up a little bit, but we will be spending a lot of time on relays because we use them so much for almost every circuit. Almost every system in the vehicle uses relays.
So, Mr. Brian, personally, is it normal that when you read the book, the CDX textbooks, and you go through them, the chapters, and then you still really don't understand a lot? like now, I've gone through the chapter, I guess, on relays, but I don't understand it.
Right. And I actually have another handout on relays that I actually really like. It's simpler. I might post it that leads with some other stuff and exercises I have that I can't do online that talk about the relays. So I will probably post that in the module as a resource. And it's kind of a quick couple-page thing that really talks about relays, but it really makes them, I think, really understandable how it explains them.
Okay, when you hear relays, I'm sorry. When I hear relay, I think of a race with, the switching.
Oh, okay. Yeah. So where you're passing the baton from one person to the next. So here I think they're using the term relay because we're using one circuit to control another circuit. So they're relaying that information or relaying that intent.
Okay. So it's normal then for sometimes everything is just flying off my head?
Yeah, it is. And I got to tell you, you guys send me questions and stuff out of the CDX book. And sometimes I read it and I'm confused and I got to back up and figure out what it is they're trying to say.
So in this schema, the first relay is controlling the 2 other relays, right?
No, in this case, the computer is controlling all the relays. The relay 1 just sends a signal to relay 2. The computer controls relay 2 and 3 and tells it where it wants that signal to go.
Yeah, that's what I meant. Sending the signal.
Right, exactly. Yeah, one relay is not controlling another relay in this case, which we normally don't do anyways. I don't need to. But we are sending it over to the next relay, then the computer decides where it wants it to go. So I do this a lot. I mean, because we're going to build on all these things. We have a whole module on just cooling systems. So we're going to get into this deeper. I kind of put a lot of this stuff here to kind of show you guys kind of the practical side of some of the stuff out there and to expose you to it. I don't expect anyone to get it 100% at this point. I really don't. But I want to expose you to it. So I find that I need to hear something probably 10 times in 20 different ways before I actually sinks in. And so that's why I kind of expose things and I reintroduce because I think that repetition is what helps us remember things.
Yep, I like that.
So in here, and I also do this to kind of show commonality. So here I have a starter circuit. And here's my ground, right? We know ground's normally at the bottom. Here's my battery. So kind of interesting. My battery comes up and this dashed line between these circles meets, this is all the same splice. So these are connected together. If I bring this wire up, it's also connected right over to this fuse. And I can see I have another fuse here. So they put the power at the top, the ground at the bottom, and I have an ignition switch. So I get power to my ignition switch, and my ignition switch, doesn't the switch kind of look a lot like the HVAC switch we use for the blower motor? It's a sweeping arm. Same kind of language, isn't it? So depending on where the arm is, that tells me where the power is going to. So if I go over to number 3, that means I want to start. So then power would come down through here, and it goes off to another page, but it also comes down to my transmission selector. So I have to be in park or neutral for power to get through the transmission switch. In the old days, you remember you used to be able to start the car in park or start it in gear and it would just lurch forward. And then in the 1970s, they came out with safety switches. So I can only get power through the switch if I'm in park or neutral. We see the lines there. Then it comes up to a relay. Here it's the load. So it's going to trying to turn the relay on. And the other side of the relay should go to ground. And if I come through the other side, yep, it goes to ground, but it goes to ground inside the powertrain control module. So even if I turn the ignition switch on and I'm in park, my starter relay may not work if my computer doesn't want it to start. So what are some reasons it might want it to start? Maybe it thinks it's being stolen. Maybe it doesn't recognize the key being used, right? Maybe the car is overheated and it doesn't want it to start because the car is too hot and it doesn't want it damaged. So there's different reasons why the computer might not want the car to start. And so then if it does work, then we see the dash line over to the switch in the relay. And the switch comes down and it's going to send power down to my starter motor. Now there's another solenoid inside here that creates electromagnetism and pulls this switch over because this is going to what? Down to the ground side of the motor. Now I have battery power. It comes through this switch that we just closed, and now my engine's cranking over. So you can see there's a lot to just when you turn the key, getting the engine to actually crank over. And that's why people go, my engine's not cranking over. What do you think it is? Well, I think it needs to be looked at. I mean, is the battery good? Are we getting a signal at the starter telling it to start? Is the starter relay working? So we can see where we go different places. Sometimes the starter is not easy to get to. Sometimes the starter is 5 hours underneath an intake manifold. I can't get to it to test here.
Excuse me, Mr. Brian. I see solid lines, bold solid lines, and dashed lines. I'm sure there's some significance as to each one of those.
Yes. So these bold solid lines are wires. These smaller solid lines are inside the junction box. The wide dash line across here, the dark one, is showing me this is a part of the junction box and not the entire junction box. The lighter dash line here tells me that this splice is all one splice, where these, you got a bullet point here, bullet point here, bullet point here. These are all actually connected at one thing. They've only spread it out for the schematic to make it easier to read. There's a laugh. So, and then this right here is fusible link wire, which is notated right here, and it gives you the
Okay, I know I asked for my last question. Let me ask one more. New
Hey, please,
schematic.
don't worry about it, Warren. I just give you a hard time.
I'm messing with you. I was told on a relay one side is the control side, the other side is the load side. And I'm looking at pin 86 where the coil is on the starter relay.
Right?
Is that considered the control side? Because it's going to a,
I would consider that, you know, and again, this is where our nomenclature gets bad. So are we talking about controlling the relay? 85 and 86 control the relay. You know, 30 and 87 go out to whatever load. So that's the switch side. So I always call this the switch side of the relay. And I call this the load side of the relay. When we start using control, are we talking about controlling the relay, in which case 85 and 86 control the relay, or are we talking 30 and 87, which control the starter? You see where, and depending on who you read and who you talk to, you're going to get some different, it gets real confusing. But are we trying to control the relay? That's 85 and 86. Are we trying to control the starter? Well, that's 30 and 87. You see where that can kind of get confusing in the language?
yeah, it kind of,
I
kind of flip back and forth because I said it's actually working, if you follow it, down to the powertrain control module,
right.
PCM. So it actually is like a load side as well, right?
Right. So I always call, at least I try to always call this the switch side and this the load side. This is the load side of the relay. This is the switch side of the relay.
Thank you, sir. Just wanted to get my brain set right. So when you say it again, I'll remember.
Right. And hopefully I'll say the same thing because I get turned around too.
Mr. Brian?
Yeah.
On the starter motor, I was looking at the relay and it has two resistors. Can you explain? I mean, I know one is supposed to be for solenoid to turn the switch on, but what is the other solenoid on the left?
Okay, these two solenoids right here.
Yes.
Okay, so there's a pull-in winding and a hold-in winding. So these are the two windings we have on a starter solenoid. And when we get into starters, I'll break those down a little bit more. But basically, this one pulls in, this one holds the solenoid in position. So I need more current flow to move the solenoid. So I have a lot of current flow, the solenoid moves. As soon as it moves, it closes the switch. This is now power. This is now power. There's no electrical difference. So this load is no longer doing anything. Oops, sorry. So then this load right here is what holds the switch closed while you're cranking it. So we use them both to get that arm to move over, boom, really fast. And then as soon as it does, we only need the little one to keep it there.
So it's pretty much like a force just to hold it in place.
Yeah.
To have more force. Okay.
Yeah. So this one holds it in place, but it takes them both to get it to move.
Okay.
So this is the pull in. This is the hold in. And the starter section gets into that a bit more, and we'll talk about it in the PowerPoint also.
So solenoid is a type of relay.
A solenoid is a type of relay, but they're broken out separate. So a relay is real defined. A relay is going to have a load side and a switch side. A solenoid can be used to switch electricity like we're doing it here, but I can also use it to put fuel in the engine and call it a fuel injector. I can use it to recirculate exhaust gas and call it an EGR valve. I can use it to change the timing on the car and call it a VVT solenoid. So a solenoid is very specific, and I'm getting a little ahead of myself, but it's very specific that it creates electromagnetic field with a plunger in the middle of it, and that plunger is going to move. So if I put electrical contacts on the plunger, then boom, it creates an electrical connection. But if I create that same plunger to a door, I can, or to a door lock, I can make the lock unlock and lock with a solenoid. I can't do that with a relay. Does that help a little bit? And again, we're going to get into them deeper. But so solenoids can control electricity, but can also control a lot of other things. We tend to use solenoids where we need to flow more current than what a relay can handle. So here, this is as hard as it gets. I don't think there's any wiring more confusing than power windows. I think this is probably the hardest thing on the car. And as I look here, I've got these relay boxes. I've got a power window motor, driver's side front. And I see electric control module, GEM. This is a computer here. I got this resistance wire that kind of says goes to C. This goes to A and B. I'm really missing a lot of the picture. And this goes to D. Well, if I look, since this goes to D and this is my motor, this goes to C, which goes to the relay. If I flip here, now I can get to where my motor is. Here's my passenger side, and I can see the A, the B, C, and D. So if I look at this motor, and we know we have to have power and ground for a motor to work. So the first thing I want to do is figure out who's power and who's ground. Well, I can see I've got G200 here's ground. It comes over, and I have ground coming through here, coming back up, and oh, I got ground here. And I got ground going here and ground going here. Well, if this is ground, I bet you A has to be power. And if I back up, and if I come to A, gee, look, A and B are both what? Power. So if I go forward again, and I've got A is power and B is power. So what these do, everything we've been working on so far has a single switch, right? We have a switch on the power side or the switch on the ground side. What we do with motors is if I want it to go one direction, I'm going to put power here and ground here. If I want it to go the other direction, I'm going to put power here and ground here. I'm going to reverse them, and I need to reverse them both at the same time. So if you notice, this switch is hooked up kind of funny here, isn't it? So what it does is it's going to shift over and allow, as we move this switch, I'm going to put power here and ground here, or power here and ground here. So you can see we have two poles here. That's why I have power coming in the middle, and I have ground on both outsides. So as we slide this switch across, I can connect between here and here on 1 and 1, or I can connect here and here, 2 and 2. And in the middle is 0, which allows me to what? Use the switch up here, which is the master switch on the driver's door, to go what? I can go over here 5 and 5, or I can go over here 6 and 6, depending on whether I want to go up and down, and it goes right through the window switch when the window switch is off. So you can see where this is really confusing, because we're not only controlling power and ground at the same time, we're controlling it from two different places. What I can tell you, power window circuits are the easiest to get turned around on and get confused, because the schematics are, aside from being horrible, they're very confusing. And to give you an idea, I was in the shop and I had my boss and one of the other technicians working on a power window system, and they'd been on it all day waiting on some parts back and forth, and it wasn't working. And they came to me and said, Brian, can you take a look at this? We've put a new switch in twice. We've done this. We got everything torn apart. It's not making sense. I look at the schematic. I take a look at it, figure out what it is, and figure out that the brand new switches they were getting from Ford were made wrong. And I actually had to cut a connection inside the switch, and then everything worked right. But here I got my boss, who's a master tech, and I got another technician working on it who's a master tech that can't make heads or tails of a two-door pickup truck's power window system for the passenger window, because they get that confusing. And this is where we use a power probe or something. So if I back probe pin 1, when I'm going maybe up, I should get power, and when I go down, I should see ground. If I go to 2, when I go down, I should see power, and up, I should see ground, right? It should be the opposite. So the easiest thing to do a lot of times is get to here and test it, or if I'm going to pop a switch out, check the outlet side of the switch. When I switch, do I get power? Go the other way, I should get ground. The other one should be the opposite. Usually what we find is the contacts have gone bad in either the power or the ground side where we don't get a good switch. But I introduced this to you. I'm never going to test you guys on this. I don't expect you to know this. Those of you that are really interested in this professionally are going to pursue. But I wanted you to make you aware it's out there, and B, let you know this is the hardest, most complicated wiring schematic on the car right here. You're looking at it.
I just want to understand, when you say power probe, what do you mean? Is it a clamp?
No, I'm going to get to that. Right after we get to this case study, I'm going to show you exactly what it is. So here I have some crazy exterior lighting. With the brakes applied, the brakes work okay. Front park lights and license plate lights also come on. The odometer and clock dim. When I turn the right turn signals on, the left park lamps and license plate lamps cycle. Odometer and clock dimmed at opposite cycles. If I turn on the hazard, all the flashers work, but the license plate lights also cycle. The odometer and clock also go bright, dim, bright, dim, bright, dim. My left turn signals work normally. When I turn on the headlights, all my brake lights come on, but my headlamps and my park lamps seem to work normally. So at first guess, this car seems possessed. But what I need to do is I need to look at the circuit for each of these systems. And then on the systems that are not working right, I need to see what component or where they share something. Because what's happening is that something is shared, a component is shared between all these, and that's where they're connected together. So my left turn signals work normally, so it can't be something that's just on my left side. It has to be something on my right side. So as I look, and I've traced in red here how each of these circuits work. And I want you to pay attention to this right rear. So I come down through the brake pedal to my high mounted stoplight and through my combination switch down to my rear stoplights. On the right turn signal, I come in power from a different place through my flasher relay, through a different position in the combo switch, down to my right turn indicator. Hazard would come down in a different position up here in the flasher, different position in the switch. And now what? We light up the front, the back, everybody, but we're not supposed to light up our license plate lights that are lighting up. If I turn on my headlamps, we come from a different place all the way down. And now I light up my license plate lights, but you see every time I come through this right rear lamp, I'll back up. See how I'm always going through that light? It's the only thing on all these that all of them have in common. When I pull the light out, I find that the filament broke and jumped to the other circuit, causing the short. So although the symptoms are overwhelming, the solution was pretty simple. Print out the schematics, highlight where everything goes, and then see what they share. What they share is where I should start my diagnosis. In this case, it was a right rear bulb. I went there, looked at the bulb, and saw the bulb was broken. Took the bulb out and things didn't work crazy anymore, just the light didn't work. So sometimes problems seem really complicated. They have a simple solution. On the other hand, where's the value? Is the value on figuring out the bulb's bad or putting a new bulb in it? I think the value is in figuring out what the problem is. And a lot of times people are like, well, you're charging me $50 to put a light bulb in? No, I'm charging you $50 because I know what light bulb to put in, and I know the light bulb's going to fix the problem, right? Putting the light bulb in isn't worth the $50, but knowing the light bulb will fix the car is.
Right, light bulb is cheap.
Yep. So here is a power probe. Back to the question. So a power probe may have a screen on it. 3 and 4 both have screens, and they have an auxiliary lead off to the side that has ground in it. So I'm able to apply ground and power using the rocker switch and light a light bulb up. I can apply ground or apply power. I have little lights and buzzers that tell me if I have power or ground here. So it tells me if I have a good connection. And it also tells me the voltage that I'm reading. So in the cable that connects this to the battery is about 25 feet long or 20 feet long. So I connect this to the battery and I can go all over the car with this. And so I can use this to power a power window to make it go up or down. I can use this to power, a seat to move it forward or back. So I can use this to not only see what's there, but if I think I'm missing the ground or missing the power, I can actually apply it by using the rocker switch and the pointer here and apply that. Or I can take the component off the car or disconnect the component and apply ground using this lead, touch the other end with this lead, use the rocker switch here to give it power, and see if the motor or light bulb or solenoid or whatever works. Isn't that more efficient than measuring it with resistance on a solenoid? Because what I really want to know is, does the solenoid click, right? Does it work? So I could what? Unplug it, connect power and ground. Does it click? If it does, it obviously works. That's better than an ohms test and quicker.
The picture here, where does the power come?
The power comes from which you can't see on here, the other end is a long lead that connects to the battery.
Okay.
And I should probably get a better picture. This is a homemade load substitution box. So you're going to hear me talk sometimes about installing a substituted load to stress a circuit. And this is also the preferred method we have if I have a short circuit for trying to find where the short is. Because the problem with a short is the fuse blows. Well, how do I find where the problem is when the fuse keeps blowing? Well, I understand Ohm's law, and I know that if I have a power supply, conductors, and a load, I have a complete circuit. So what we'll do, and here's the wiring on how it's built. What we'll do is we'll take the fuse out that keeps blowing, put the load substitution box in, and all the light bulbs light up bright. When I fix the short, the lights are going to go out or get really dim. I'm not buying a bunch of fuses. I'm just putting that in. And then all I got to do is make the light bulbs go out to fix the car. That's a lot simpler than keep putting fuses in and hoping I got it, isn't it? But what have I done? I've just made a different circuit, haven't I? From power through my load to ground. When I get rid of the ground, the light bulb goes out. So a little different way of finding shorts, much better than a cycling circuit breaker or using fuses. So this is just a tool. We also have sensor simulation tools. So our Decade box has different resistors in it. So if I need to put resistance in a circuit, I can do that. And MI has ones, tens, ohms, hundreds, and thousands. And so sometimes I can use that to test wiring back to a computer for a sensor. So if I think the sensor is bad, I can plug this in instead of the sensor and see if the scan tool now reads the right number. If it does, it proves all the wiring's good and the computer's good, and I just have a sensor that's out of calibration. That's a lot quicker than ohming out all the wires or checking all the wires, isn't it? So same with using simulators. Different circuit fault finders for open circuit or short circuit. Power Probe makes a tool. This is old school here. Snap-on sold these. And this deals with electromagnetism. The concept being that if I have a shorted wire, when I run this down the wire, the arrow is going to show me the direction of current flow, and I can come up and find where the short is, because I'm not going to have any current flow after the short, right? Some old school stuff. So these are back probing tools. So these are those little needles I was talking about that we go into the back of connectors with to hook a meter to.
Got a little question.
Yes.
What's the name of the Power Probe?
Power Probe. And the one I recommend is the Power Probe 3.
3. Okay. That's the one who got the screen, right?
It has the meter. It doesn't have the full screen. The 4 has the full screen. If you're looking at the 4, you can buy it. Snap-on also sells it, and you can buy it with a Snap-on label and Snap-on warranty for the same price as the Power Probe 4 on eBay, and get the Snap-on or Amazon and get the Snap-on warranty through the student discount. So that if you're looking at the 4, look at that. I think the three is real good. The 4 does more stuff. Do you need it? I don't know. I haven't played with them. I like the 3 a lot.
Okay.
Right?
Because I'm looking at on Amazon and
Yeah, Amazon has the Power Probe 3s.
the 3. Okay, so is it better that start with the 3 or should I go straight for the 4?
I think the 3 is probably adequate. I still use the Power Probe 2 at the shop, which doesn't even have a meter. And I do like the Power Probe 3 a lot better. Look at the features and benefits on the 4. If you think you'd like the 4, try it. I've had a couple students buy it and they like it. You know, I think the 3 is more than adequate. But up to you. Again, sometimes things are adequate because it's what we're used to. Like I said, I haven't used a 4 in the shop yet. I've used a 3 quite a bit.
Okay, thanks.
I like the 3 a lot. I like the 3 better than I like the 2. I don't even know if you can still buy 2s. But I've played with the 4 a little bit in the shop, and it's a neat tool. It does a lot of neat things. I don't know if the neat equals fixing cars because I haven't played it with it enough. So these are front probing tools, kind of like what we see down here with this J tool, where we're what's called drag checking a connector. We're checking fitment of the pin. So these are adapters to go to a meter, so I can actually build a harness in the middle of a connector. So when we talk about drag testing, what we do is we'll put something into a connector and it should hold the weight of the connector. If the connector falls off, that means the pins inside the connector have opened up and won't make a good electrical connection. So a lot of what we see on cars today is bad connection issues because someone didn't use these front probing tools. Instead, they went in and jammed their meter tools in there trying to read voltage or read whatever and have actually destroyed the pin, causing a problem. That's why we back probe so much. These little loops right here are for measuring current. So what you do is you take the fuse out of the fuse box, you plug this in, you plug the fuse from the fuse box into the side of it, then you could use your inductive clamp on this loop to measure the current in the circuit. So these are kind of slick. These are those relay testers I was talking about. So what you do is you unplug the relay. This plugs into the relay box right here. The relay plugs into the top of this, and then you have your pins. And it's kind of hard to see, but you can see 86, 30, 87, 87A, and 85 here. So these are numbered, the same numbers the relay uses. So now I can hook a meter to it. I could use a power probe. I can do all kinds of things and watch and test the circuit with the relay connected because this is plugged into the relay box. The relay is plugged into the top of it. And then I can do all my testing. And you'll see me do this in the cooling system demonstration I do. I actually use one of these. But these are one of my favorite tools. Just because they're so quick and easy. And they're not, oh my goodness, expensive. I think the whole kit for all 8 of these, plus some other tools, is around 120, 130 bucks. And that covers all the different relays out there. So it's a pretty slick set. Made by Lisle is a company, L-I-S-L-E. So this just talks about different adapters that we have. Sometimes there's pre-made test harnesses, male to male, female to female adapters. You know, I have a whole drawer in my toolbox of just different leads, adapters, connectors, things like that for the different stuff I do. A lot of times we end up having to build a harness or build a jumper harness to do testing. And this is that wire chart that I showed you guys previously. So this is the end of the test PowerPoint. I'm going to open up the module for batteries, module 3. I'm going to open that up. I'm also going to turn on a couple of quizzes in Canvas for this module 1. One is a PowerPoint review quiz. Recommend doing that first. And the other one is a quiz on the whole electrical module, asking you guys to apply a little bit of what we've talked about. So I'm going to turn on both of those. Today's Monday. I'll probably put them both due by end of day Thursday. So don't worry about killing yourself on a quiz today. I know we got a lot of stuff going on. I'm going to turn on module 3, which is batteries and starting and charging. So we're going to get that turned on, and we're going to start getting into batteries tomorrow. And tomorrow, I'm going to break it to you that our 12-volt batteries are not 12 volts. But I use 12 volts because the math is easy. So we'll actually get into and find out that if your 12-volt battery only has 12 volts, it's actually dead. And talk different ways about how to test the battery. So on that note, I think we're good for the day.